and remote. It's a pleasure to introduce Chris Petersen, who is today speaking to us from the University of Florida, who is probably sheltering a little bit through some hurricane activity. Currently, everything is looking good. But while Chris is an assistant professor at the University of Florida in Gainesville, and he's leading the Spacecraft Research and Technologies Laboratories at the Department of Mechanical and Aerospace Engineering. And before that, I met Chris when he was at AFRL RV, and we worked for several years on a project. And it's a pleasure to have him here. And I guess the stage is yours. Chris, take it away.
Wonderful, Ricardo. And thank you all for having me today. I wish I could have joined you in person, but a couple things prevented that. But today I will be talking about designing, developing, and deploying model predictive control for satellite rendezvous and proximity operations. And so, as Ricardo had said, my name is Dr. Christopher Petersen, but I go by Crispy, like Krispy Kreme, Crispy Chicken, Crispy Donut, whatever floats your boat. But let's kind of get into things. So just as an outline of what I'll be talking about today, I'll introduce these set of problems that I focus on at the University of Florida and previously what I did at AFRL, and really kind of set the stage. And the set of problems I look at is called rendezvous and proximity operations. And I'll go through how, when I was at AFRL and how I'm continuing here at looking at designing model predictive control through three separate phases, what I call design, develop, and deploy. And I will kind of reference a little bit of what I've done in each one of those areas, and with some concluding remarks and answering some questions. So to set the stage a little bit, the first space age, this was in the mid 20th century. And in this sort of first space age, it was really driven by governmental interests, primarily the US and the USSR. And in the 1970s, we roughly had around 1,500 objects in space, 7 nations really operating out in that regime, 2 nations to the moon, but a lot of the focus was either close in on Earth or just landing someone to the moon, nothing in between, and maybe thinking about sending a satellite very far out beyond our solar system. But the aspects of controlling a vehicle in space were very narrow at the time. But now let's flash forward to what I call the second space age, which we're living in now. And this is partially driven by governmental interests, those still persist, but it's also driven by a lot of industry. If you look at Amazon and SpaceX, they're sending up thousands of satellites to facilitate wireless internet or some of their own interests. OneWeb, which was also going to send up 1,000 satellites before they went bankrupt, had a lot of interest in trying to create their mesh network. And that was primarily around LEO orbit, which stands for low Earth orbit. But then you had a series of other satellites expanding past close to Earth, going into the geostationary regime or geostationary orbit. This is where your satellites that provide GPS are sitting. And there's a variety of objects out there. There's lots of interest around the moon, to the point where now in 2020, we have almost a factor of 2 greater amount of objects in space, 20,000 and counting, with just short of 80 nations in space and 7 nations to the moon. And there shows no signs of stopping this entire push. But because that there's so much of this interest in space, there's a lot of interest in the research that goes forward and how we can push state of the art to help a lot of these interesting problems. So maybe just to kind of create a nice little icebreaker, let me kind of tell you what I have done in the past. And this chart was from my times at AFRL. So what my mom thinks I do is I'm a crazy scientist. And that's not necessarily false, but it's not necessarily true as well. I don't have the crazy hairstyle, but a lot of the research that I look at has a flavor of craziness to it. We couldn't extend state of the art if we didn't think crazy, if we didn't think far ahead of the curve. And that's something that is very prominent in the space industry because we have to think that way. What my friends think I do, I'm an astronaut. That's kind of the most common thing if you look at the International Space Station. And I would never be an astronaut, if only because of the fact that I'm deathly afraid of heights, but not exactly false in the sense that that sort of research that I look at, and especially in terms of automation, optimization for satellites, has to have some sort of flavor of human interaction with it, has to have the human trust whatever is going on so that they're able to float in space without worry. What society thinks I do works with aliens. In my previous job at AFRL, I actually worked for Area 52, which was right next to Area 51, but I am contractually obligated to say that I can neither confirm nor deny the existence of aliens. What my boss thinks I do, I build complex systems like this Star Destroyer right here, but not necessarily false in the sense that a lot of the work that I did at AFRL and still persist at University of Florida is looking at how I design algorithms, machinery that interact with other sorts of subsystems in a way to effectively create a big satellite that can operate autonomously. And all those subsystems have to act appropriately. What I think I do, MATLAB, research, really pushing those bounds. But what I feel like I do, and one of the things that I actually do enjoy, is make PowerPoints, because it's a way for me to convey the research that I have been involved in and that I continue to push forward, as well as kind of looking at how we can start extending state of the art past where we are currently. And all this to say is that a breadth of experience is needed to perform basic research and deploy it. So I have 3 words that I'll get into a little bit later: develop, deploy, and design. And those each kind of have to go with a different flavor in the design process. Now, setting the stage a little bit more specifically, space research is as large as the universe itself. What I tend to look at are problems which we call rendezvous and proximity operations. And those missions really are when satellites fly in similar orbits and fly within roughly 500 kilometers of one another. And this is the regime which we call proximity operations. Satellite companies such as Amazon or SpaceX, they like to set their satellites very much farther apart on the order of megameters. These sorts of operations are a little bit more closer. And we see them most commonly in aspects of docking. So for example, if you have the ISS, you see the Dragon capsule coming up to dock, that is a rendezvous and proximity operation. There are other aspects in this regime, aspects of servicing and repair. If you look at the Mission Extension Vehicle, or MEV, by Northrop Grumman, they actually went up and refueled a GEO satellite, and that was a proximity operation. That sort of domain is starting to get a little bit more exciting. You have coordinated maneuvers. We have aspects on the ground, terrestrial-wise, of UAVs, and a lot of people are thinking about, how do I extend that to the space domain? Those sorts of operations are inherently RPO. You have scientific experimentation. If anyone has heard of the GRACE mission, that was a scientific experiment to measure gravity waves. And primarily, anything about space is primarily dominated by science. We would like to think that guidance, navigation, control is the primary thing on any satellite. It's not, it's the science. Orbital debris mitigation is a topic that's becoming very, very common, as well as manufacture and aperture creation. So there's a lot of different aspects for proximity operations, and it just doesn't have to deal with docking. Some missions that I like to highlight, there's the ISS docking with another satellite. A mission near and dear to my heart was an Eagle Mycroft, which were 2 satellites flying within proximity to one another. That's a mission that I worked on personally. You have RSGS, which is a DARPA mission meant for servicing other satellites. And you have NASA's Argonaut 1 mission, which is meant to manufacture apertures. All this to say is those sorts of missions really require a lot of fine tuning and a lot of interesting design aspects. For example, looking at things in not an inertial frame, but in a relative frame. And I'll get into that a little bit later. That's what these images here. But all of these missions require precise, quick control, typically on the span of 1/8 of an orbit, which for objects near the ISS, that pretty much corresponds to control mechanisms on the order of minutes. In geostationary orbit, we have a little bit more flexibility, controlling maybe once every 5 minutes if you're not that close, but you need a lot of precise maneuvering, which is why techniques like model predictive control are rather convenient. For those who are not familiar with MPC, this sort of control technique it looks over a finite horizon and continually optimizes a cost subject to constraints. And so, for example, if you look at the diagram on the right-hand side, you have an initial location in the star, which is your final position. You optimize a trajectory at that time instant, and it goes straight across to the star. Now, you only execute one portion of that trajectory, and you see where that lands you. And because all models are wrong, some are less wrong than others, because of unknown disturbances or some other factors that you might not be accounting for, that trajectory is not going to closely follow what it desired. So at that second time instant, you re-optimize, you re-look over that horizon, and you come up with a different path. And you do this at multiple discrete time instances, nominally at some constant frequency, and what you get is an ever-evolving path. Now, MPC has numerous benefits. The design process is rather systematic. It's rather straightforward. You can optimize a cost function that you've defined as a user, subject to state and control constraints which reflect safety. And because you are doing this re-optimizing process, it is responsive to changes in the environment. But what it is not is always computationally efficient. Optimizations in general cannot be performed on millisecond levels unless they're finely designed. And continually optimizing is not always stabilizing. You have to think about what your cost function is, what the constraints are, in order to enforce this sort of stability. Model predictive control might not always be optimal. And what I mean by that is you might reduce the problem to something that's easier to solve, but doesn't give you the optimal solution to your original cost function. Or you might not even converge to the optimal solution you want. And furthermore, it's not always intuitive. So what do? Well, in order to combat what it is not, we carefully design the problem, and we develop this via iterations between basic research, applied research, and deploying it. And we deploy it with users in mind, i.e., we can design all the fancy autonomy we can, but if it's not trusted or known by the person who's using it, it's just going to stay on a shelf. So one of the things that I've realized is that MPC is a nice blend of stabilizing control theory and optimization. It's fairly efficient and useful for safe maneuvering. And if phrased appropriately, it's rather intuitive to a user. So it checkboxes all of that. So this talk today is roughly going to go over a little bit more of the intricacies to think about when you start looking at MPC and some of those considerations you might want to take a hold of when you're designing it for particular applications. And these considerations, I've been into 3 categories, which I call design, develop, and deploy, which can be thought of theory, application, and implementation. And for the design phase, this is where you start thinking about theory. This is thinking about what model do I use? What metric do I use to minimize this? What are the constraints? A very common thing we think about in control, is this resulting feedback loss stabilizing? And will the value function decrease? Those sorts of things which people don't often think about if they're just saying, let me recursively optimize this function. Then you get into the develop phase. And once I've formulated a nice problem, what do I use to solve it? What are the speed and memory constraints that I am dealing with? What are the convergence properties of the thing that's actually solving the problem? And that's often a decoupled process. And one of the things that I very much like to do is look at the intersection of those two. And then finally, the deploy phase or the implementation is, okay, now that I've designed it, what are the inputs to this algorithm? What are the outputs? How do I command this? How do I display the data? Which might seem trivial at first, but for a user who wants to basically deploy MPC and use it, those things are important. And there might be inputs and outputs, which we as control engineers might not typically think are important, but might actually increase the breadth of MPC far past what has been initially envisioned. And I'll get into that a little bit later. But all that to say is that an iteration is needed between all of these phases. And if it's done this way, what I've seen, at least in terms of model predictive control, is it really starts pushing this technique past what anyone had imagined. So let me get into at least these three phases and show you what I mean. So let me start with the design phase. So in the design phase, this is where we commonly think about how we formulate the problem mathematically. And so as control engineers, one of the things we think about is what is the right model? As George Box had said, all models are wrong, some are less wrong than others. So what do we choose? Now, there's two models that people like to commonly choose for rendezvous and proximity operations. The first is a nonlinear model, which is called the two-body equations of motion. And in this case, there are some relatively mild assumptions in this model. Gravity is the only acting force. The mass of the Earth is much greater than the mass of the satellite. The Earth and the satellite can effectively be treated as point masses, and that there's no mass loss. Those are some relatively simplistic, but some nice assumptions that generally hold. And if we look at this lends itself to a very nice nonlinear model, which is shown by those differential equations. But this model does not have any closed form solutions if you start putting in control actions in it. So what that means in the entire scheme is we could use those dynamics, but we have to make sure that we understand we use numeric propagation to basically show those trajectories as they evolve over the finite horizon of MPC. So it's great for missions requiring large maneuvers or more precise maneuvers, but it requires time to propagate. Likewise, you could actually make a couple more assumptions and get something a little bit easier, a linear model. And there's a typo there. I really need to get that fixed. But by making two other assumptions, basically that two satellites are flying pretty close to one another, i.e. 500 kilometers, and that one of those satellites is in a circular orbit, you actually get a set of linear dynamics. Those are called the Hills dynamics or the Kahetzi-Wiltshire dynamics. And because they are linear, we can then exploit all those nice properties that come with it. Controllability, observability, almost closed form solutions for propagation. But because there's more assumptions, these tend to be not accurate over long periods of time. So we can exploit the linearities, but we're going to have to perform things at a quicker rate to make sure that those differences don't manifest themselves detrimentally. All that to say is that in a lot of RPO aspects, everyone likes the linear model. And for that, as long as your MPC control loop is sufficiently fast, typically less than an eighth of an orbit, the linear model is actually very useful for our control practices. So for MPC and optimizing, that's what we typically go with. But that's not to say that we can't use a nonlinear model for other applications. And in fact, for some MPC, that becomes more advantageous, especially if you're looking at satellites over longer time durations. But in my experience, the linear model has always been useful. But always when you say optimization, you have to think, what am I optimizing over? And while that might be intuitive to some, others it might not be. So very commonly, people like to think, I want to get my satellite to the position as quick as possible. Well, that can be formulated as minimum time. So typically that's formulated as a mixed integer programming problem. Mathematically stated there, it's great for time critical missions, but the value function, which is basically a function that as you move your state around, what is the optimal of that? That value function is a stepwise function. It's very choppy, which is very, very hard for a lot of numeric solvers to actually find a solution to if you don't use the right one. And furthermore, you get something like a control profile of a bang-bang solution, which some people like and others hate. It's great for time critical missions. It's terrible for fuel, and it's very hard to solve in real time. Okay, so now let me just look at minimum fuel. Well, I can write it as a quadratic cost, get there as efficiently as possible. It can be solved by a quadratic programming problem. And the value function is decently nice. You can see it there on the bottom left-hand side in the middle box, but it doesn't necessarily have a unique minima. It has a well, which can be a little bit difficult for some solvers to get a solution to and can actually lead to discontinuous control. So it might be great for fuel critical missions, but because of this discontinuity in the control action, it might be terrible for stability and robustness, which is why a lot of MPC policies tend to go with the LQR cost, which gets you your nice quadratic cost, it gets you your unique minima, it gets you a nice smooth control profile, great for stability, efficiency, and robustness, but does not match the ideal mission. If you ask a person their objective for a satellite, they will say, get me there with the least amount of fuel, because fuel is paramount. There's no gas stations in space. But no one's going to say, hey, I want less fuel, but I also want to minimize error, unless you're a control engineer. So choosing the right cost functional is important for the mission. And not only that, but also important to understand where it leads to stability and robustness. So oftentimes we've seen LQR works perfectly well, but we've also done minimum fuel and minimum time MPC, if only for the fact that our operators really wanted those two. And it might ruin stability and robustness, but there's some other things that we can recover in that. And then my final aspect in kind of this design phase is, how do I choose the right constraints for the mission? And typically in satellites, we think about safety as being paramount over anything else. So we have keep out zones. Do not crash and damage the satellite. Well, that can be reflected by a quadratic constraint. You have max control, which can be reflected by a norm. You can also have a unique constraint, which is an exclusion cone. It's called lighting. And so if you assume that one satellite is always looking at the other, you don't necessarily want to consistently look at that satellite and then have the sun in the background, if only because of the fact you might damage the sensor. That can be really reflected as a cone constraint, exclusion. Or if I'm getting closer to my satellite, don't go too fast. That's called a range rate constraint, and it's a fairly nonlinear one. All that to say is, as you choose your constraints, you then kind of choose the complexity of the problem. And all that to say is, you should not fear complexity, especially with MPC. You can make a nice quadratic program and solve it really efficiently, but if it doesn't solve your goal, then don't use it. Don't restrict yourself to fancy linearities. And that's what we found, at least for spacecraft applications. You have to dip your toe into nonlinear. And then you can also have some nifty terminal constraints. You can say arrive at this particular orbit at this velocity. That's a nice, well-known terminal constraint. You can also say approach in this cone, and that leads itself to a nice set of other nonlinear constraints. But understanding how these are actually formulated and how to mathematically describe them is key to ensuring operational success. And that was something that we've learned in designing MPC problem formulations, is what we think of from a control perspective might not be what the user wants or where it's going to be deployed as being that operational constraint. And that could be the difference between someone using it and someone not using it. And just as kind of an example of where this actually comes into play, this was a collaboration with my former advisor, Professor Ilya Komanovsky at University of Michigan. And this was a rendezvous and proximity operation maneuver where if you didn't take into consideration coupled translation and rotation model, and you used just a relatively simplistic one, you would actually crash into the satellite that you were trying to rendezvous, which is that video up at the top. But if you were able to understand the full model that was needed, you were able to understand the constraint that was actually being formulated, and if you were actually able to understand the cost, you could formulate this to guide your satellite to rendezvous and not crash into one another. So all this to say is that in this case, we weren't afraid to use the nonlinear model, and we were able to exploit other properties like the cost and the dynamic and some convexified constraints to improve performance, to get us to get that quick control rate. So that's how we kind of look at design. Let's take a look at the develop phase. And this is really once I've mathematically formulated my cost, my constraints, my model, how do I solve that problem in MPC? Because that's what I'm doing. I have to solve an optimization. And my big takeaway for everyone here is really you need a solver that is correct for the mission and works with, not against the problem formulation. A lot of people in the model predictive control regime either just say, let me mathematically formulate my problem and let me have a black box solver just solve it. That's great for prototype, but is absolutely terrible for real-time applications because that problem might not be able to be solved by that black box. So that's not to say that you can't use a black box. It just goes to say you have to understand what goes underneath the hood. And so two types of solvers or optimization techniques that I look at for these types of things can be binned into nonlinear and quadratic linear solvers. Nonlinear solvers are basically those solvers that you can give it a generic cost functional, a generic constraints, and you can solve it. It's great for nonlinear aspects of costing constraints. It's great for complex objectives. And there's a great number of techniques like sequential quadratic programming methods or SQPs, particle swarm, simulated annealing. There's techniques like GPOPs out there that can solve this. That's great, but they're awful for time rapid control. It could take anywhere on the order of several minutes to several days to solve a poorly posed optimization problem, which is not good for rendezvous and proximity operations. Also, nonlinear solvers can be terrible for consistent solutions. If you are using something like a particle swarm method, the same initial guess into the solver might result in a completely different solution. And to someone who wants to execute an MPC path on a vehicle, like a satellite, and they say, well, let me double check this trajectory by running the algorithm again, and it gives them something completely different, that is a roadblock to ever implementing that algorithm ever again. So, but that being said, nonlinear solvers are nice if you have complicated objectives. Then you have quadratic linear solvers, QPs, simplex methods, linear accelerated gradients. These are great for simplistic objectives, consistent solutions, speed and memory. So if you need something that executes really rapidly, this is where you go. But if you're trying to solve a rendezvous problem with several keep out constraints, this might not be the way to go because it doesn't deal with complicated problems well. And solving the general case is impossible with these, but it's good to have in your back pocket. Now, add this to the fact of what's unique about satellites. Satellite technology is 10 years behind terrestrial technology for processors. You cannot send your MacBook in space. The current state of the art is what's called a RAD 750 board, and that's because it can survive in space at basically for 2+ years, and it can only do that because it's shielded by the radiation. Its memory is on the order of 100 megabytes, and its GNC speed is anywhere between 1 to 10 hertz. And even though you might be able to have up to 100 megabytes of memory total, the GNC layer really only gets 10 megabytes, if not kilobytes of memory. So for those of you that might not think that's a problem, if you're doing a quadratic problem and you're using large matrices and you're doing things with memory wrong, you can explode it tremendously to be using gigabytes. So even a QP solver, if designed inappropriately, can blow past your budget. And to give you some comparisons of where this actually lends itself, we wrote a QP solver and we executed it on our MacBooks, and then we executed it on a spacecraft processor with C code. On our MacBooks, it was 1 millisecond of execution, and on the spacecraft processor, 2 to 10 seconds. Okay, a factor or 2 or 3 of time, but still relatively quickly. How did memory get impacted? Well, 1 to 5 megabytes of memory, that was good within our available budget, but when it was put onto the spacecraft processor, it used 10 to 100 megabytes of memory, blew past our budget completely. So all that to say is that designing this problem here especially when you're trying to choose what solver you're using, you have to not only consider how fast something is going, but understanding the memory usage. And that's not necessarily to say that you shouldn't be using quadratic solvers or nonlinear solvers. It's choosing the right thing for the job. And for RPO methods, we found that you can frame quadratically constrained problems and quadratically costed problems to be fairly efficient on the order of 1 to 2 megabytes. But you have to think of things like how accurate can be computed and how consistent that solution needs to be. It's a very intricate problem. And so we tend to lend itself to something that's quick and memory efficient. And something that, kind of goes along the same lines, I call it computation throttle MPC, but I'm sure Ricardo might call it something different. This was a collaboration with Don Husting Schultz, Paul Wintz, Sean Phillips, and myself. And this was looking at aspects of how do I take a cost functional and reframe it as a dynamical system? And then how can I solve that dynamical system rapidly? And one of the things that we've been seeing is that there's this parameter alpha here that really starts to really increase computation or decrease it. So by playing with this alpha term, we can really start understanding, okay, if I have the time available to compute my solution, change that alpha parameter to a certain point where I need to get a solution quickly, but it might not be as accurate. Or if I have all the time in the world, dial it the other direction, and I can slowly converge the solution accurately. So this is an example of taking the problem formulation, understanding how it's solved, and actually exploiting that for computational resources. Now, the last phase that I really do want to touch on is called the deploy phase. And this is something which gets into the implementation aspect of things. And as I said at the beginning of this talk, when we command MPC, typically in code that's framed as kind of this one-liner, MPC execute, you give it its inputs, and it comes as an output. Now, for control engineers, we typically think as inputs, especially for path planning, as position and velocity, and the output should be only the thrust at the current time it needs to execute. That's very common for just traditional controls. But what if we had access to a number of other constraints, a number of other inputs or outputs? So for example, what if we increase the inputs to be something like number of thrusts? So I could effectively have my algorithm or my optimization process decide how many number of thrusts there are, or decide what the timing between those thrusts are instead of having it recompute at a constant rate, or how well it checks the constraints and how well those have to be obeyed by. Those sorts of things which really tend to lend themselves to being hard-coded. Then if we think about it as being part of the actual control architecture, we then open the breadth of MPC tremendously. If it has the ability to change these things, then you could come up with new efficient solutions that were not thought of before. Or you could come up with more accurate solutions to rendezvous with the satellite. A very common example is that we found that by giving the number of thrusts as being a parameter for the optimization to kind of play with, we were actually able to increase efficiency by a factor of almost 10%. And we were still able to reformulate the problem to get us our stability. There's also aspects of what needs to be an output. It doesn't just have to be the thrust at the current time. Why not the entire trajectory? Why not also the cost value and maybe something that says, hey, did my solver converge or not? One property that I find very interesting to feed back into the control system of MPC is the cost function. Because one key indicator if MPC is stabilizing is that cost function should be decreasing over time. If it's not, then there's something going wrong. But if we have access to that cost functional, you might be able to feed back that into the MPC policy and actually start to improve efficiency that way. And then there's some other things that have been useful for MPC. I have this thing called the diagnostic table, which is basically a bunch of parameters that says, hey, did my solver convert? Operations did it do? That gives a nice indication for me to see if it works. But one could conceivably think of having the diagnostic table be fed into the loop, and if things don't work, recompute it. So all this to say, if we broaden our scope of what becomes an input and an output to MPC, the sky starts to be the limit. And the way that we can start exploiting the system starts to manifest its way in unique aspects. And one way that we've seen this happen is in a collaboration with myself, a student called Sean Rice, and Dr. Bechet Akamis at University of Washington, is we started playing with this implementation where MPC traditionally has to compute at a certain frequency. But what if this MPC policy only had to recompute when it needed to? So for that to happen, it needed access to outputs of what is my solution, what is the trajectory of my solution, and how close am I following it? And how it triggered was my trajectory still safe? If so, great. Was I following that trajectory? If so, great. And if the trajectory, ensure that the trajectory doesn't end, if all three of those were satisfied, then great. But if I wasn't following my trajectory correctly, recompute it. That had necessity to understand what that entire trajectory was, as well as what the cost was over that trajectory. And what we found in this sort of implementation is that we could trigger this MPC policy when it needed to, and it incurred a cost of about 10% more, but it reduced computation by 3 times. And this lends itself to being able to be utilized for more complex MPC. If we can reduce computation, then we can use more complicated solvers, more complicated problem formulations. So this kind of starts showing that MPC has a great theory associated with it, has a great theory with the solvers, but if you start understanding how it's implemented, then we can actually start playing with that and really pushing the bounds of MPC. So let me get to a couple of conclusions here. And really all this to say, I went through a lot of material at a very high level, and I love MPC theory. I love how I choose solvers, and I love how it gets deployed. And there's benefits in trying to understand each of those aspects. In the design phase, all I have to say is being aware of what that problem is and how it best fits the mission. In the development phase, how are you conscious of what solvers you use, and how can you exploit that for either computational gain or efficiency? And then the deployment phase, how do you understand how it's being deployed to maximize the potential of a satellite? Now, when Ricardo asked me to talk, this all has to deal with cyber physical systems. And this really gets into that aspect. How do we take the mathematics that we derive on a daily basis? How do we make sure we understand what's being done from the aspect of the optimization? And then how does that get deployed on a physical system? And if you continue this iteration through design, develop, and deploy, you start getting an algorithm that really starts to, like I said, push leaps and bounds beyond what anyone had thought of. And to end on this, we did something similar like this process on some of our current satellites. We implemented MPC and we got efficiency that we thought, but then we started pushing that bound, and we used MPC for aspects such as fault recovery or aspects of actual automated decision-making, things that we didn't think of, but we actually got to that point only because we considered these 3 steps. So might have overwhelmed a lot of people because that was a lot of material, and I realized I just went through that really quickly. But at this point, I'm happy to entertain any questions, and thank you all for your time.
Great, thanks for the great talk, Chris. Questions from the room here in the physical room?
I have a question. On slide 15, when you went from, you said the memory footprint increased from 5 to 10 megabytes to 100, 10 to 100 megabytes. Was that just because you re-implemented it? You were using a different implementation of the solver that was less efficient for this space and memory usage? Or what was the cause of that pretty significant increase?
Yeah, so you can look at it from the lower and upper bounds here. So the 1 to 5 megabytes was using a lot of MATLAB's intricacies of memory usage and how it can reference things. But to deploy a solver from MATLAB into an actual embedded system, you need C++ coding or C coding. So oftentimes you can basically do what's called auto coding that system. And if written poorly, MATLAB's memory usage, when it does auto coding, it doesn't do what's called pass by reference that well. And so if the solver is written poorly, if you're passing matrices through functions, the upper bound of that memory explosion was because of that, because matrices had to be continually recreated and stored in static memory was the reason for that 100 megabyte usage. You got down to 10 if you were able to write it in MATLAB in a little bit more efficient manner. MATLAB has an ad hoc way of C++ coding in terms of classes. And if you wrote it like that, a lot of the memory overhead starts to decrease tremendously, which is where we got to the 10 megabyte bound. But you did incur some memory usage, if only because of the fact that MATLAB still had to statically allocate variables that honestly, if you wrote it in C++, you could probably get it down to 5 megabytes of memory. But it all has to deal with how the code was written and how memory was being utilized. Pointers become your best friend when that's the objective you want to go for.
So a follow-up question for that. Can you put memory as a state of your algorithm and then keep it bounded within a threshold?
So that's a very intriguing question, and I would love to, start pushing those bounds. One could actually start looking at that because a lot of the input parameters that we typically think of as being static do have an impact on the memory usage. So, for example, if we started looking at this deploy phase, the number of thrusts actually does impact the memory. And so if you actually started studying the system or the processor almost like a dynamical system, and you had the inputs here really feeding into the computation, you might be able to find ways of bounding memory usage, which would be almost kind of a nice new flavor of how computation plays into control theory. But that would be an interesting way of seeing how can I bound memory in the same way as what people tried to do in bounding time of computation.
I don't know where the microphone is. Okay. Did you actually go through and re-hand code the algorithm in C or C++ to bring the MPC down?
On one of the missions, no, because I didn't have time to do that. I had to jerry rig it in MATLAB. But in another mission, I did actually write it in C++. And I tried to get it down as much as I can, and I only got it down to about a megabyte. But for that particular mission, I actually had a very stringent memory usage. I had only about 24 kilobytes of memory. So in that case, that goes back to maybe this chart here, is I couldn't really use a quadratic problem solver because the memory, even to the best of my ability, I can only get it down to a megabyte because of matrices. So by using something like a linear accelerated gradient, I was able to get that memory usage down to about 20 kilobytes. But yes, I've done a lot of coding in terms of MATLAB, and I've done a lot of hand coding of C++ in order to try to make that memory limit. Sometimes it works, in which case great. And in other times, if it doesn't work, then it doesn't work in the deploy phase, and I have to either consider all right, do I choose a different solver or do I choose a different problem formulation that maybe gets me less variables at the end of the day?
Other questions for Chris? Maybe from the Zoom room? Anybody there?
I have a question. You said that the systems on the satellites could only last for max 2 years, I believe you said, because of the radiation. What happens after those 2 years? Do they just shut it down, the satellite, or replace it, or what happens then?
Yeah, so maybe let me clarify on that. Rad 750s boards are meant to last 2+ years, and typically they last for 10 years. So one of the things that we have to consider in computation for satellites is radiation. We're relatively protected here on Earth because of our atmosphere, but as soon as you start leaving the atmosphere, your processors will get hit by radiation. So for a lot of low Earth orbit satellites, those are in the domain of the ISS, they actually don't use these, what we call radiation hardened processors. They use things like GPUs and NVIDIA Jetson cards, if only because the fact that they know that their mission is only going to last maybe 6 months. Because if you put a regular board on a satellite in LEO, that board will probably last 6 to 8 months. And then at that point, to answer your question, basically the satellite loses its brain. And so at that point, the satellite will go into a tumble. And presumably if it's in low Earth orbit, it'll start to lose altitude and burn up. And that's actually what has to be designed into satellites. They have to have a disposal plan. And for most times, low Earth orbit means they just burn up and we don't see anything. Now, for satellites that are in geostationary orbit and beyond, that's where you see these radiation hardened processors. They have a shielding around it, which prevents them from that radiation being hit, but they still only have a limited time span. Now, typically that radiation harden increases size by a factor of 3 to 4, weight by a factor of 5, and power by a factor of 3. And so you can think about it, if you want your satellite to last longer, you need these processors to last longer, but that comes at a cost. And so when they do inevitably fail, the satellites need to have some sort of plan. And typically that plan is for things geo and beyond. You typically stay in a circular orbit. You won't tumble in any case, and you just basically put your satellite into what's called a graveyard orbit. The graveyard orbit for geo is roughly 400 kilometers plus or minus, and that's where all the dead satellites are. When their processors are dead, they just stick around there, and it's a garbage belt. It's a dump, for lack of a better term, and they just stay there. That's one of the ongoing problems that we have in the space community is at a certain point, that dump is going to grow tremendously and we need to figure out what to do with it. But all that to say is that when if that processor dies when you don't expect it to, then you have a problem. And that question is hard to answer.
As a processor, I mean, even before the lifespan is over, I imagine you would sometimes get like bit flips and things, which maybe are just handled at a hardware level, but are sometimes computations like not trustworthy, or especially as like the processor nears the end of its life, you have to like adapt for or identify that it's failing somehow?
Very good question. So bit flips do occur, and typically satellites are equipped with what we call a fault detection and correction system, an FDC. So a lot of satellites are looking for certain aspects that we know fail occasionally. Typically bit flips will propagate themselves pretty rapidly through a system, and you'll start to see measurements and other data flows just being spouting nonsense. And so in those cases, you're able to rapidly identify them. And then the quickest solution, as funny as it is you turn off and on the satellite like you would like your internet router. So those things can be fairly infrequent at the beginning. And towards the end, they can happen a little bit more rapidly as the shielding kind of degrades. Those things aren't inherently looked at quite as much, but then you also have other things that go wrong in the system that you might not be looking at. And those computational aspects are overflows. If you have a variable that's a single and it overruns itself and it feeds into another subsystem, that could have detrimental effects, in which case the common solution to that is just, again, turn on and off the satellite. But a lot of those things happen in ways that you never predict. We will never figure out how to account for everything. We try. But when that does happen, it requires a knowledge of where the subsystem actually came up with that erratic value and how to fix that. And sometimes that can be patched by a software update. But very commonly, a lot of these computational things aren't really monitored as much. The only thing that really is monitored, or one of the things, is CPU usage. If a satellite gets up to a certain CPU usage, and you can track that, it'll actually automatically reboot to save itself. If a process is taking more than, say, 95%, it'll track that and say, oh, I can't spend any more resource. Something wrong is happening. I need to shut down that resource the best way I can. And so it reboots itself. So that gets into aspects of how can computation then influence how I make optimizations or model predictive control? And maybe how can I feed that into the process? If I see my CPU usage going up, how can I feed that into an MPC policy and change the optimization parameters to lighten the load? So parameters like that you monitor, and that's pretty well established. Other things like bit flips and overruns, you just have to hope your system is designed to catch them. And if not, well, best case scenario, your satellite's recovered. Worst case scenario, you have a piece of junk floating in space. I'm not sure if that answered your question, though. Did it? I might have gone on a rant, and I apologize.
Yeah. Covered it, yeah.
Thank you for your talk. I have a quick question for you.
Yeah.
We'll actually have two questions. Maybe I missed it and you mentioned it. Do you consider any debris avoidance strategies when solving your MPC problems? That's the first question. And the second one is, I saw this online in which when you have linear constraints and quadratic costs, you can solve your MPC as an explicit MPC in terms of computing multiparametric quadratic programming. So basically what you do is that you partition the state space into regions, and based on where each of the constraints are active, you just define a feedback law for each of them. And I don't know if you have seen that, and do you find any value in doing that versus solving online the QP? What do you think?
Yeah, so great questions. Let me start with the second one because that one's now fresh in my mind. So explicit MPC is a wonderful tool. And if you're able to partition the space appropriately, I think that's a very great way of getting a rapid solution. One of the things but there's no free lunch. So with regards to explicit MPC, while you might get the computational speed very much down because you partition that space into a closed form solution, your memory load might be a little bit more heavier, if only because you now have to define what those partition spaces are. And that might increase it to a certain extent. That's not to say that it can't be within the budget, but that's one aspect that I see with explicit MPC. The other aspect is how responsive it is. If you just have constraints that you know are static and will be pretty constant throughout your entire time horizon, like maximum fuel constraints, for instance. Let me go back to this. Like that max control constraint is a pretty static constraint. And even range rate constraints or lighting safety can be posed in such a way that you don't need to have any knowledge and they don't need to be time varying. So as long as your constraints aren't time varying and you have the memory budget, I think explicit MPC is a wonderful way to go. The downside, and probably this gets to your first question if I heard it correctly, is what do you do when you start looking at the collision constraints? And those can be abstractly kind of mentioned as time varying constraints. And if those collision constraints don't vary with time tremendously, you could do an explicit MPC methodology. But one of the powers to having MPC online is if you have constraints that vary with time, or you have constraints that you might have to turn on and off, or you have constraints that you know the basic form, but you might not know where the center of that exclusion zone is starting. Though that is where I see explicit MPC slightly failing, unless you have the ability to communicate to the ground rapidly enough and then re-upload your explicit MPC policy. And then to get to your first question a little bit more, a lot of my avoidance constraints, I kind of flip between two different ways. The first way is I do convexify them. I use rotating hyperplanes on a lot of my non-convex constraints in order to get a conservative but feasible solution. And if you rotate those hyperplanes in ways that you ensure feasibility, that's a good way of encapsulating those collision constraints. The other way that I do it is I just take the collision constraint as is and I stick it into a nonlinear solver. I am very much of a proponent that you should not be afraid of nonlinearities, and you should have a solver that should understand that they exist and how to kind of get around it. So I tend to look at solvers like SQP methods, and I augment them to be feasible. So there's a type of optimization called feasible SQP. If you're able to encode your collision constraints in such a way that it fits that methodology, you might not get an optimal solution, but you'll get a feasible solution. And that, in my mind, me being an optimal control person, I will take feasibility over optimality any day of the week. But I guess maybe to summarize the first one is if I use a QP formulation, I tend to go with convexification via rotating hyperplanes. If I do nonlinear, I tend to do the complete nonlinear formulation, but collision avoidance is a vast field. I've also played with like mixed integer linear programming, diffeomorphisms. The sky's the limit. Does that answer your questions?
Yes, thank you so much.
Okay, and we have interrogated you enough. Thank you so much for the great talk, and thanks everyone for coming online and coming in person. Next seminar. Thank you, Chris.
Yeah, thank you so much, and have a good afternoon.
If you have a few minutes, why don't you take a 5-minute break and then we'll connect back on this link. I'll be at my office for a little bit and we can chat a little bit. And then I think Paul can join as well. Yeah, so.
Sure. I'll just leave my computer on and I'll stay on this link.
Okay, we'll be back in 5 minutes or so.
Copy that.
Guys, feel free to take